In this video, we're going to look at the relationship between f and f inverse. We know that if x equals f inverse of y, that's the same as saying that y equals f of x. So if I substitute f of x for y in the equation on the left, I see that x is equal to f inverse of f of x. That is, if I compose the two functions here, if I first apply f and then apply f inverse, I get back to x again. And in the same way, we know that the equation x equals f of y is the same as saying that y equals f inverse of x. If I substitute f inverse of x for y here in the equation on the left, I get f of f inverse of x equals x. The formula f inverse of f of x equals x shows that the work done on x by the function f is reversed or undone by the function f inverse. Likewise, the work done on x by f inverse is also reversed by applying the function f. Let's look at an example. So we've already worked out the inverse or formula for the inverse to the function f of x is 2x plus 1 over x minus 3. So we have f inverse of x is 3x plus 1 over x minus 2. So let's check out our composition formula. If it's correct, which it should be, we should have f applied to f inverse of x should give us x. So how do we calculate this composition of functions? Well, f applied to f inverse of x, we start from the inside out. We write down our formula for f inverse of x, and we apply f to it. This is the same as saying f of 3x plus 1 over x minus 2. How do I apply f to this formula? Well, I look at the formula for f, and everything that's inside the brackets here should replace x in this formula for f. F applied to this is 2 times that plus 1 over that minus 3. When I tidy that up, I get this fraction here. It boils down to 7x over x, and then I can cancel the 7's to get x. And as predicted, same thing happens when I calculate f inverse of f of x. In that case, I'm looking at f inverse applied to 2x plus 1 over x minus 3. I take the formula for f inverse and I replace every x in that formula by 2x plus 1 over x minus 3. Now it's simply algebra, and when I tidy it up again, I'm left with 7x over 7, which is x. The concept of an inverse function that undoes the work of a function is quite intuitive. Think of what happens with message encryption. If I want to send a message to my friend that says, I love math, but I don't want anyone else to see the message or know what it says, then I need to encrypt it somehow. And I might first replace the letters of the alphabet, A replaced by 1, B replaced by 2, and because that's a very simple code, I might then apply the function f of x equals 2x plus 1 to each number that I get. And that gives me a code. A becomes a 1 first, and then when I apply f of x equals 2x plus 1 to it, I get 3. B becomes 5, C becomes 7, etc., etc. And now my coded message looks like this. I becomes 19, L is 25, O is 31, etc., etc. So I send this to my friend, and rather than carry around that cumbersome table, my friend just might want a simple way to decode the message. And in order to do that, she needs to reverse the work that I did on those numbers x with the function f of x equals 2x plus 1, and she can do that with the inverse function. When sending this message, it's crucial that I use a one-to-one function to translate those initial numbers to a new number, otherwise there's going to be ambiguity in the message and it can't be reversed. So recall that to find an inverse function for f of x, to undo the work that I did on each of these numbers with f, we first solve for x in y equals f of x, and when we do that, it's simple algebra, we get x equals y minus 1 over 2, and now we know that that's f inverse of y, and we switch the x and the y to get a formula for f inverse of x. So f inverse of any number is that number minus 1 over 2. So to decode this message, my friend needs to take each of these numbers and apply this inverse function to them. So for example, if they take this first number, f inverse of 19 is 19 minus 1 over 2, which is 18 over 2, which is 9, and this gives the 9th letter in the alphabet, which is I, etc., etc.